Hello, today we're going to be talking a little bit about coordinate geometry to go through some of the things that you probably recall from Algebra 1, but we're just going to dig a little bit deeper in them and see what you remember, what you don't remember. Okay, so first off, remember you've got your four quadrants. So like running the bases in baseball, 1, 2, 3, and then 4. Obviously you know that. Each point in this Cartesian plane is made up of an A and a B. An x value, and that's how far over you're coming, and then a y value, how far up and down you're coming. We generally label a point with a capital letter just to avoid confusion, just consistency across math and geometry. Again, a review of some of your algebra skills. We have the midpoint formula. Midpoint formula finds the point that's directly in between two given points. It essentially acts as the average of the x values and then the average of the y values. The distance formula, we get this nice big complicated formula. But another way of thinking about it is that if you have a starting point and an ending point, if you connect them with a segment, you can always make a right intersection between those two. Whether it's above or below doesn't really matter. This distance over here is the change in the x values. This distance over here is the change in the y values. If you want to know how long this segment is, it's just a Pythagorean theorem to be able to figure it out. Well, the crazy part is it's the exact same math as the formula. I just find this a little bit easier to remember. Alright, so let's take a look at this. We've got a 2x minus y equals 3, and we're going to try and present it in three different styles. In equation style, generally we like y equals mx plus b. So I got to shuffle things around a little bit. Maybe I can subtract that 3 from both sides. Maybe I can add y over to the other side. Technically speaking, the way you originally encountered it, 2x minus y equals 3, already is an equation. It's just a little bit nicer to follow convention and have that y equals mx plus b. As a table, we can again go back to that Algebra 1 background. You learned all this stuff back then because it's super important, and you can continue to leverage it way deep into a master's in mathematics should you need to. Make up a couple x values, whichever ones you might like. I'll pick nice, easy, convenient ones. And then plug those x's in to find out y's. X is referred to as the independent variable, y is the dependent. Negative 1 times 2 is negative 2, minus 3 is going to be negative 5. I get a minus 3. 2 minus 3 is going to be negative 1. You might even just notice a pattern in the y's that are going up by 2. Once you got a nice table, you can graph. Oh no, my first one's out of bounds, so maybe we'll just ignore that. And then go 1, negative 1, 2, 1, 3, 3. Absolutely everything you encounter in mathematics, whether they're nice straight lines, whether they're curvy quadratics, or even trig functions, exponentials, whatever you might possibly encounter in math, all of it has these three versions. You can always look at the equation, the table, and the graph to try and understand what you're dealing with a little bit better. If one of the formats that you're encountering is not bearing any fruit, it's not working out for you, you could always switch formats and analyze it in a different way. It's a huge trick that's really great to take advantage of in calculus. X and y intercepts. So here we've got a squared on our x. That means that we're dealing with something a little bit more complicated. It's not a line. It's going to be a quadratic. It has an intercept of negative 2. If you're not sure what this looks like, make your xy table and try and analyze a couple x values to be able to get an idea of what it looks like. I happen to know that it's going to be a nice classic quadratic, like that, and they want to know what are my x and y intercepts. The y-intercept is this guy right here. That's where it crosses the y-axis. Y-intercepts are always going to be in the format of 0, comma. If I plug in a 0 for x, as if I'm looking at it on this table, 0 squared minus 2 is negative 2, and I find my y-intercept. My x-intercepts are these guys. They're a little bit harder to spot. I don't see them as cleanly on my graph, but I can know that they're also always going to have a 0 in them. It's just in the y spot. If I bring that 0 over into the y spot, I can now do a little bit of solving to find out what x is. Add 2 to both sides, and then square root. Don't forget, whenever you square root, you have to include that plus minus. Pure algebra, it's really easy to forget that. It doesn't seem like it's all that crucial to life. But when you look at the graph, if I don't include that minus, I can't explain that left-hand side. It's really built into the problem that I need to include that plus minus in the problem. So my x-intercepts are plus or minus root 2, comma 0. Sketch and define region defined by that. Well, that's not something you encounter very often. The squiggly braces are referred to as the solution set. They're letting you know that where the problem answer starts and where it ends. XY just represents any ordered pair. Every ordinary coordinate, like we saw, P is some XY pair. This line up and down is read such that. It's defining how I'm going to define what this XY coordinate is. I want all the points where 2x is less than 8, or x is less than 4. So I come to 4, I'm not including it, so I'm just going to do a dashed line. And I want every point where x is less than 4. So like this point would count, that point would count, this point over here would count, this point right there would count. I don't even have to be on lines. Any point in there, they're all good points. So I denote that just by shading in this whole region. All of those points are coordinates where the x value of that coordinate is less than 4. More complicated one, here we've got a set of rules for the x's and a set of rules for the y. My absolute value of x has to be less than 4, which means if I'm looking at a coordinate on the graph, the x value has to be less than 4, just like before. But it's also got those absolute value bars in it. So like if x was 2, that's perfectly fine. If x is 0, that's perfectly fine. If x is negative 3, the absolute value turns it positive, which would be okay. So it's actually going to have me stopping at negative 4. Because once I go to negative 4, then I'd be out of bounds. So anywhere in this region is happy right now. But I only want y values that are bigger than 3. Dash that guy out. And now I have this whole region of the graph. Those are all my feasibility region. Circles. You obviously know what circles are. Don't forget their algebraic formula. X squared plus y squared equals r squared is the definition for a circle that defines this guy right here. That circle assumes that your center is at the origin, and r is the radius of how far out you're going with that circle. If you want to move your circle to a different locale, so that this guy's at coordinate 1, 3, then you have to go to this translated h, k version, where my h would be 1 and my k would be 3. And can still have the same radius, it could have different radius, it really doesn't matter. It just allows us to put our circle absolutely anywhere. The endpoints of the circle are right there. I'm a visual person. I like to draw pictures when I'm looking at a problem like this, just to try and understand what I'm looking at. This is my p sub 1, and I've got a negative 312 somewhere up here. I'm not trying to draw to scale. I'm not trying to get the exact location of it. I just need to have a point of reference. They tell me that I'm talking about a circle, so maybe it's going to look something like that. And I'm trying to find the circle's area. If I'm trying to find the area of a circle, I know that that is pi r squared. So I'm trying to get the r value of this problem. I got two different ways that I can approach it. I could either find the full diameter between those two guys and cut it in half, or I could try and find out where the center is. And once I know where the center is, I could go from the center to either edge. Both work absolutely fine. I'm going to try and use the idea of the diameter. So my change in my x values is going to be 3 to negative 3 is 6. My change in my y's is 4 to 12 is going to be 8. And I'm just going to use that Pythagorean theorem trick we talked about before. And I find out my diameter is 10. My diameter is 10, that means that my radius is going to be 5. And I know the area of the circle is pi times 25. Or, as we normally write it, 25 pi. Slope. Slope is rise over run. You might have seen it before in the past as delta y over delta x. The delta is a Greek symbol that we use in math and science to represent change. So it's the change in the y value, or a rise, divided by the change in the x value, or a run. Slope allows us to describe the path of any line. We always read slope from left to right, and you probably have encountered this formula before to actually calculate slope. If you have your two coordinates, you can take the difference of the y values over the difference in the x values. Ultimately, it doesn't matter which order you go, so long as you're consistent with 2 and 1. Now, this you might not have seen before. This is a harder slope problem, very much befitting pre-calc. This crazy graph has different slopes at different times. So I can't simply just ask you what is its slope. Instead, I have to give you a location. So I have to ask you what is the slope of this crazy graph at 1. If we go to 1, we see right there that it's a flat horizontal segment. So its rise is 0 and its run is 1, which means that has a slope of 0. At 4, right here on this kind of slanty segment, on the slanty segment, we have a rise of 1 and we have a run of 1, which means that this has a slope of 1. At 9.1, it's pretty hard to pinpoint. I can't use that as a coordinate the same way I did here to be able to count out boxes, but it's part of this segment. The whole segment has the same slope, whether I look at this precise crazy decimal or whether I go to nice integer coordinates to be able to measure it. Here I have a rise of 1 and a run of 2, so that's a slope of 1/2. At 8, I'm at a little bit of a conundrum. This guy is heading down, this guy's heading up. So because there's two different choices, I say that this slope is undefined. I can't actually explain it just because there's two different choices as to what it could be. Quick review of some of the special cases. I'm looking for the equation of a line that is perpendicular to that line and passes through the origin. Basically, when trying to figure out slope, there's only two things you really want to know. Lines. You need to know the slope and you need to know the y-intercept. This perpendicular is going to help me get the slope. If I shuffle this around a little bit, 4x plus 5 equals negative 6y, and y equals negative 4 6x minus 5 6. Its slope is negative 2/3. If I want to go perpendicular to that, I have to use opposite reciprocal, which means I flip that upside down and I change its sign. This is the slope of what I want. The y-intercept means absolutely nothing to me. The whole purpose of this equation was just to extract the slope that I needed. I'm passing through the origin, which means that I have a y-intercept of 0, 0. And my line is just going to be y equals 3/2 x plus 0. An equation of a line that has a slope in that and goes to that. Now here you could force this and say 1 equals negative 3/2 times 4 plus b, and force the y equals mx plus b. But it's much nicer to use point slope in this problem and just say y minus 1 equals negative 3/2 x minus 4. And that's done. You don't even have to restructure it to make it y equals mx plus b. Alright, so this is a crazy problem. The best approach is to draw it. If I look at this point, 3, 1, L1 equals 8 is kind of like saying y equals 8, and that's just giving me a horizontal line. L2 is parallel through that 3, 1. When you see it as a picture, it's very easy to see that L2 is also a horizontal line with a height of 1. So I could just say L2 equals 1. The slope of L2, because it's a horizontal line, would just be 0. The y-intercept of L2 is just the coordinate 0, 1. Once I have the picture of what's going on in the problem, it's a lot easier to answer it. Alright, so this is just a word problem. We've got this set up. We get a nice equation explaining what things are, and they ask us to graph this. Big y-intercept, slow slope. It's going to look something kind of like that. This is at 28. What do the slope and the w-intercept represent? Slope in this problem is change in y, which is your amount of water, over change in x, which is time. So that's basically change in water height over time. Slopes always have two parts, like miles per hour, some kind of a changing unit. And then the w-intercept, which is the y-intercept, is the starting amount. Alright, there's an activity for this. It's also built in through our Canvas. I'm sorry, but I'm short on time, so I'm just going to have to stop here. I hope you learned a little bit.